Hey, welcome to the Electronics Lab. In this video, I am going to analyze this circuit. And this is a question from the online textbook that you can find in the links below. And basically what you need to do in this question is come up with the Norton equivalent for this part of the circuit so that you can figure out the voltage across and the current through this load resistor. So I'm not going to go through any of the theory, I'm just going to jump right into this analysis. So the first thing to do in a circuit when you're trying to convert or trying to determine the Norton equivalent is identify what part of the circuit that you want to do that for. And it's really defined in the question already. It's this part of the circuit and this is the load. So what I can do is remove the load and then label the ports in the node just so I can keep track of them through the analysis. Not really critical for this particular circuit because it's fairly simple, but if it was more complicated, that might be fairly important. The next thing to do is to figure out the Norton resistance. And that's the resistance seen between points A and B. So the Norton resistance is equal to the resistance between A and B. And in particular, it's that resistance when all of the sources are set to 0. So in this case, we've got two voltage sources, and when I set a voltage source to 0, it becomes a short. So that source becomes a 0, becomes a short, and this source becomes a short. And now it's a fairly simple analysis to figure out what that resistance between A and B is. It's simply 4 kiloohms in parallel with 10 kiloohms in parallel with 2 kiloohms. 1.18 kiloohms. The next step is to figure out the current between points A and B when I have a short circuit there. And I need to put the sources back into the circuit to do this part. And a short A and B. And now I want to figure out what is that AB current. And that AB current is the Norton current. Now for this analysis, what I'm going to do is use superposition. I've got two voltage sources, and so I'll analyze it with a 10 volt source, figure out what the AB current is, and then analyze it with a 24 volt source and figure out what the AB current is. Add those two numbers together, and that will give me the Norton current that I'm looking for. So first, looking at the 10 volt source, when I'm looking at the 10 volt sourse, the 24 volt source becomes a short. So I'll ignore that 24 volt source. And what I will draw the short. So I've got 10 volts across, well, look at this. AB shorts out the 4 kiloohm and the 10 kiloohm resistors. So the only resistance that I see, the only part of the circuit that will actually have current will be this outside part. And that IAB current for the 10 with the 10 volt source is going to be minus 10 volts divided by 2 kiloohms. Because look at the polarity of the voltage source and look at the direction I'm defining AB current to be. So that's why it needs to be a negative number. And so this works out to minus 5 milliamps. Now I'll do it with the 24 volt source. I'll do the analysis with the 24 volt source. So I need to put the 24 volt source back and remove the 10 volt source. The 10 volt source is removed. It gets shorted because it's a voltage source. And the current AB, due to the 24 volt source, well, again, look. That short between A and B shorts out the 4 kiloohm and it shorts out the 2 kiloohm resistor. So the only current in the circuit will be in this path. So there's only that 10 kiloohm resistor in the path that the 24 volt source is providing. And that works out to 2.4 milliamps. So the overall AB current will be the sum of those two. It will be the sum of those two currents. So I've got minus 5 milliamps plus 2.4 milliamps, which works out to minus 2.6 milliamps. So I have the Norton current and I have the Norton resistance. The last thing I need to do is redraw the circuit. Since it's a negative current, or redraw the circuit in the Norton equivalent form. Since it's a negative current for the Norton current, the current's actually going downwards relative to the rest of the circuit. And in parallel with that source is the 1.18 kilo ohm resistor. And there's my 2 points A and B. And if you remember what was in there for a load, we had a load resistor in there with a value of 12 kilo ohms. So now that we have the simplified Norton circuit and added the load back, now it's a simple matter it's a simple analysis to figure out what the voltage across that 12 kilo ohm load is and what the current through it is. So let's figure out the voltage across the load first. So the voltage will be that negative 2.6 milliamps times the parallel combination of those two resistors. And that works out to minus 2.79 volts. And now that I have the voltage across that resistor, very simple to figure out the current through it. That equals minus 0.232 milliamps. And that's it. I came up with the Norton equivalent. I put the load resistor back in the circuit. I did my analysis to figure out the load voltage and the load current, and I've got my two values there. And if you go ahead and check out the video in the link here, I think it's going to be here, you can see the exact same circuit analyzed using the Thevenin equivalent, and you can see I get the exact same values. All right, I guess that's it. Thanks so much for watching. See you in the next one.